In this lecture, we discuss about complex number. Let us first see what is the history and origination of complex number. The concept of complex numbers originated in the 16th century when Italian mathematicians like Gerolamo Cardano in 1505 to 1576 and Raphael Bombelli 1526 to 1572 attempted to solve cubic equations. These equations sometimes required taking the square root of a negative number which had no real solution. Initially, complex numbers were seen as imaginary and had no physical meaning. However, in the 18th and 19th century, Leonard Euler, Carl Friedrich Gauss, and Augustin Louis Cauchy developed a solid mathematical foundation for complex numbers. Gauss introduced the complex plane, which allowed complex numbers to be visualized graphically. Today, complex numbers are fundamental in engineering, physics, electronics, and many advanced mathematical theories. Now, in this part, we discuss about the complex number and its introduction. A number of the form x plus iy, where x, y are any real numbers, is defined as complex number. If z is equal to x plus iy, then x is called a real part of the complex number z and y is called the imaginary part of the complex number z and is denoted by r of z, real part of z, and I of z means imaginary part of the z respectively. If x is equal to 0 and y is not equal to 0, then z is equal to iy is called the purely imaginary complex number. If x is not equal to 0 and y equal to 0, then z equal to x is called purely real complex number. Complex conjugate of a complex numbers. The complex conjugate of a complex number z is equal to x plus iy is defined as the number z bar which is equal to x minus iy. So if you want to find out the complex conjugate of any complex number x plus iy, we have to just replace I by minus I, then we get its complex conjugate. For example, the conjugate of z equal to 3 plus 2i is z bar equal to 3 minus 2i. Geometrically, it is the reflection of the point z in the x-axis. Algebra of complex numbers. If z1 equal to x1 plus iy1 and z2 is equal to x2 plus iy2 are any two complex numbers, we define following rules and laws of operations. Equality. Two complex numbers z1 and z2 are said to be equal if their corresponding real and imaginary parts are equal. That is, x1 is equal to x2 and y1 equal to y2. So we say that both the complex numbers are equal. Addition. z1 plus z2 is defined by sum of real part plus sum of imaginary part, means x1 plus iy1 plus x2 plus iy2. So we have to add the real part to real part and imaginary part to imaginary part. This is called addition of two complex numbers. Subtraction. So Z1 minus Z2, which is given by x1 plus Iy1 minus whole bracket x2 plus Iy2. So we have to subtract real part to real part and imaginary part to imaginary part. So this is called subtraction of two complex numbers. Then multiplication, Z1 multiplied with Z2 is given by x1 plus Iy1 multiplied by x2 plus Iy2. It gives us x1 x2 minus y1 y2 plus I times of x1 y2 minus y1 x2. This is the multiplication of two complex numbers. Similarly, division of two complex numbers z1 upon z2, which can be written as x1 plus iy1 plus x2 plus iy2, which is given by x1 plus iy1 upon x2 plus iy2, and let us realize it with the conjugate of x2 plus iy2, means we have to multiply by x2 minus iy2 and divide by x2 minus iy2. And now if you multiply those two things, we have x1 x2 plus y1 y2 upon x2 whole square plus y2 whole square plus I times of y1 x2 minus x1 y2 upon x2 square plus y2 square. So this is the division of two complex numbers. Commutative law of addition and multiplication. So Z1 plus Z2, which is given by Z2 Z1. This is the commutative property with respect to addition. Similarly, Z1 into Z2, which is equal to Z2 into Z1, is the commutative property for multiplication. So both are true in case of complex number. Associative law of addition and multiplication. So Z1 plus in bracket Z2 plus Z3, which is equal to in bracket Z1 plus Z2 plus Z3. So this shows the associative law of addition. Similarly, Z1 times of Z2 Z3, which is equal to Z1 Z2 whole times of Z3. So this is called associative axiom or property or law of complex numbers for addition and multiplication. Distributive law, Z1 whole multiplied by Z2 plus Z3 is equal to Z1 Z2 plus Z1 Z3. So this is called distributive property. Some important formula. First, Z plus Z bar, which is equal to 2x. Z minus Z bar, which is equal to 2iy. Third formula, real part of Z equal to 1 upon 2 Z plus Z bar. Z bar means conjugate of Z. Imaginary part of Z equal to 1 upon 2i Z minus Z bar. Fifth property, modulus of, conjugate of Z1 plus Z2, which is equal to conjugate of Z1 plus conjugate of Z2. Sixth property, conjugate of Z1 minus Z2 is equal to conjugate of Z1 minus conjugate of Z2. Seventh formula, conjugate of Z1 Z2, which is equal to conjugate of Z1 into conjugate of Z2. Conjugate of Z1 upon Z2 is equal to conjugate of Z1 divided by conjugate of Z2. So these are some important formula based on real number, complex numbers. Now, in this part, we see what are the different applications of complex number in engineering. So first application is in electrical engineering, like AC circuits. Complex numbers are used to represent voltage, current, and impedance in alternating current circuits. For example, Ohm's law in AC circuits uses complex impedance V is equal to IZ, where Z is a complex impedance. The second use in the control system engineering, the stability and behavior of systems are analyzed using complex numbers and Laplace transforms. For example, Transfer function analysis helps design stable automatic control system. The third application is in the fluid mechanics and aerodynamics. It is used to model the flow of air over airplane wings and fluid flow in pipes. For example, potential flow theory uses complex functions to analyze fluid motion. The fourth applications of the complex number is in signal processing and communication system. Complex numbers helps in analyzing the designing ratio, TV, and digital communication systems. For example, Fourier transform uses complex exponentials to analyze signal frequencies. The fifth applications is in robotics and computer vision. So complex numbers used for 2D and 3D transformations, including object, rotation, and scaling. For example, a robot arm's movement is controlled using complex number transformations. The sixth property is in civil engineering, structural engineering, and vibrations. It is used to study resonance, damping, and oscillations in buildings and bridges. For example, damping analysis of earthquake uses complex numbers. The seventh application is in quantum mechanics and physics. Schrodinger's equation uses the complex numbers to describe the behavior of quantum particles. For example, wave functions in quantum mechanics are represented as complex functions. Eighth application is in image processing and computer graphics. It is used in age detection, transformations, and noise reduction in images. For example, Fourier transform filters improve image clarity. The ninth application is in the artificial intelligence and machine learning. Complex numbers are used in neural networks, deep learning, and pattern recognition. For example, wavelet transforms are used complex functions to process AI signals. The 10th application of complex number is in astronomy and space science. So it is used in orbit calculations, gravitational wave analysis, and radio astronomy. So these are some main applications of complex numbers. Thank you.